All right, calculus, here we go into section 3.6. And this one is a little bit more like what the rest of chapter 3 is going to look like. We're actually learning how to take the derivatives of new styles of functions here, which is most of our goal here for the duration of this chapter. And now we're moving away from polynomial functions and we're getting now into the derivatives of the trigonometric functions. And this is a good opportunity for me to kind of warn you guys a little bit that for those of you who were a little bit annoyed that we had to go back and relearn the formal definition of derivative, you know, the whole limit as h approaches 0 and yada, yada, yada. A lot of you guys felt like that was unnecessary because you learned the shortcuts last year for taking derivatives. But, it is a foolish person who thinks they know and doesn't know. No, a wise person knows what they don't know. Something like that. Anyway, the point there is that the shortcuts that you guys learned last year for taking derivatives only work for one particular style of function, most notably polynomials. And those shortcuts that you learned for polynomials do not help you at all when you move into non-polynomial functions, of which there are a lot out there in the world. So today we start talking about the derivatives of trig functions, and your power rule shortcuts don't really help you at all. Okay, to get into this, everybody, there are two trigonometric limits that we need to know, and they are listed right here, and they are listed right here. But before I even start talking about them, let me calm your fears here, everybody. You absolutely do not need to know these ones for a quiz or a test. This first one right here is the one trigonometric limit that we did talk about back in chapter 2. The limit is h approaches 0 of sine of h over h equaling 1. And remember, guys, this graph is a little bit inaccurate. I did graph it on my calculator, but the domain of this function, sine of x over x or sine of h over h, does not include the value of 0. So there's actually an open dot. Oh, that was poorly drawn. There's actually an open dot right there at the point 0, 1. But this statement here is still 100% true because, let's go back to the idea from chapter 2, a limit doesn't care about what y value your function reaches, it's only asking what y value it approaches. And then likewise, the same thing happens with this limit right over here. Now this one we used far less than the first one. I think I did put it in your notes back in, what was that, guys, section 2.6 or 2.7 maybe, I'm not sure. And I think I told you at the time, hey, we're going to need this really quickly in section 3.6, and sure enough, here we are. Once again, I think you guys can tell, you can't put a 0 in for h in that function, or you end up with a 1 minus 1 on top, which of course is 0 over 0. So once again, this function has an open dot there at the origin, but the calculator graph doesn't really show that. We're going to need both of these two ideas in order to move forward with what we are really going to work on. So here we go, guys. The very first thing we're going to do in this section, and relax, good news, this is the only time we're going to do this the hard way, is we are going to use the definition of the derivative that we developed earlier on in this chapter in 3.1 to find the derivative with respect to x of the most basic trigonometric function we can come up with, that being sine of x. And I honestly can't remember if you guys learned this last year in pre-calc or not. If you do, shh, don't tell anybody the answer. All right. And if you did learn it and you do remember it, I still want you guys to see where this comes from. I don't want you to think that some mathematician just conjured this out of a hat or just made something up. So if we want to try to find the derivative with respect to x of sine of x, well, here's what I think we probably need to do. The function we're dealing with then is sine of x. That's the function that we are differentiating. So I'm going to go ahead and name that here to the side, f of x. And what we're really trying to find now, guys, is the derivative of that function here, so f prime of x. And the definition of the derivative, we haven't used it in a little while, so I'm going to go ahead and write it out, is the limit as h approaches 0 of the difference quotient now, f of x plus h minus f of x, there's the change in your y values, over, and remember guys, the denominator is really x plus h minus x. But as soon as you say that, I know you guys know you can simplify that. X plus h minus x just becomes an h down there on the bottom. So that's the definition of the derivative, and let's see how that relates to this particular problem now. So f prime of x, that's the derivative that we're looking for, is equal to, and here we go, the limit as h approaches 0 of, and now the first term in the numerator, f of x plus h. Well, we look at the original function right here. And everywhere that there was an x, we now replace the x with the binomial quantity x plus h. So this is going to become the sine of the binomial quantity x plus h. That was easy to write, guys. That's it for f of x plus h, and then minus f of x, which is just the original function here, which is the sine of x. And of course, we still have an h down there on the bottom. We should always be thinking about plug and chug, but sure enough, if the h actually becomes 0, you get sine of x minus sine of x, which is actually 0, all over 0, and 0 over 0 is an indeterminate form, and that doesn't work. So what we now need to do is really the same as what we were trying to do before, guys, with polynomials. The problematic factor in the denominator, which is h, needs to be eliminated in order for us to be able to do plug and chug. However, the numerator now, while it still does need to be written in a different way so that we can eventually get rid of that h, all the tricks that we did earlier on in this chapter with polynomials, things like expanding the square or the cube of a binomial and using the distributive property and combining like terms, those things aren't really relevant here because we're not talking about polynomial functions. We're talking about the sine of the sum of two numbers right here to give us our new angle, x plus h. And to pull this off, everybody, you need to know an identity that you talked about, definitely last year in pre-calc, maybe the year before in Algebra 2 as well. And the identity that you guys learned is the sum identity, that the sine of the sum of two angles. It is not as simple, you guys, and I sure hope nobody's going to suggest this here, as distributing the sine here to make sine of A plus the sine of B. That is not the way this works. You can't distribute an operation. You can only distribute a number, and that's not what's going on here. So this identity, which I'm not expecting you guys to remember, and I will not ask you to have memorized for a quiz or test, was that the sine of a sum is equal to, nope, not that, Mr. Fontana, was equal to the sine of one of those angles, A, multiplied by the cosine of the other angle, B. And then we add to that kind of the opposite now. The sine of the other angle, sine of B, multiplied by the cosine of the opposite angle, which would be A. So this is an identity that you guys learned at least last year, if not 2 years ago also. And while you don't have to have it memorized, we do need to know it in order to make sense about what's going to happen next, where we try to rewrite, I don't really want to use the word simplify, but rewrite the expression sine of x plus h. So where are we, guys? F prime of x is equal to, we're still not ready to evaluate this, so this is still a limit as h approaches 0, but now this numerator gets messy. So the sine of x plus h is going to become the sine of the first angle times the cosine of the second angle plus the sine of the second angle, that's sine of h, multiplied by the cosine of the first angle, which is x. Now the order you do that in, guys, does not matter because all we're dealing with here is addition and multiplication, both of which are commutative. But let's not forget we still have this minus sine of x at the end just kind of hanging out there, so that goes there. And of course there's still an h on the bottom. It certainly doesn't look like we made this numerator simpler than it was, but we did get rid of the messy thing that we had right here, which was the sine of a binomial. So where in the world are we supposed to go from here? Well, once again, if we let h actually become 0, we still have this 0 down in the denominator, so we are not ready to plug that in just yet. We still need to do a little bit more up on top, and this takes a little bit of creativity in order to see where we're going next. All right, guys, what I want you to notice is that your numerator contains 3 distinct terms. I'm going to put them all in red parentheses. The first term, sine of x times cosine of h. The second term, sine of h times cosine of x. And the third term is this sine of x at the end. Out of those 3 terms, 2 of them contain a common factor of sine of x. This one and this one. So I'm going to take advantage of that, and I'm going to rewrite this in a way that might not be intuitive, but I'm hoping in just a moment you're going to understand why it is that we wrote it this way. So f prime of x is the limit as h approaches 0 of, okay. Now what I'm going to do mentally, you guys, is put this term and this term right next to each other. And then we're going to factor out the common factor that they both possess of the sine of x. Then in parentheses, what's left from here is a cosine of h. And what's left from here, after you pull out the sine of x, is a minus 1. Now, this middle term isn't in on the joke. It didn't get a sine of x, so it just tags along at the end here. So that's just plus the sine of h times the cosine of x, and that's still all over h. Now, I don't think that that's abundantly clear, you guys, why we did that yet, but hey, relax, we're not done just yet. What I am going to do, everybody, let's see if this works. I'm going to copy that. I'm going to go over here to this next page, and let's see if I can paste it right there. Okay, look at that. Look at me go. All right, so that is where we left off the last page. I'm going to get rid of this identity here, guys. We don't really need that anymore. All right, so this is where we're at. Now, how are we getting closer here to actually evaluating this limit? Well, let's see what's happening next. Okay, so we are now going to say that the f prime of x right here is equal to, and I'm going to keep the limit right here as h approaches 0, but now we're going to start to get a little bit interesting. I'm going to put a big set of brackets right here. And what we're going to do is take advantage of the fact that my numerator right now is really two big terms. That is one term in the numerator, and that's a second term in the numerator. So I'm going to write this now as basically this term right here with the h on the bottom, sine of x times cosine of h minus 1 all over h. And then I'm going to do plus this term right here, sine of h cosine of x all over h. However, in doing that, I'm going to take a little bit of a liberty right here, and the sine of x I'm going to pull out in front of that fraction. So, dang gummit, okay, this is the sine of x. And that's going to get multiplied now by the cosine of h minus 1 all over h. That takes care of all of that. Plus, now in the second term here, guys, I'm going to pull the cosine of x out in front. And what's left in parentheses there? We've got a sine of h in the numerator and an h in the denominator. Close those parentheses. Close those brackets. Now what you guys might notice is that I pulled out a sine of x here and a cosine of x here. I pulled out the factors that contained x because remember guys, we're taking a limit right here as h approaches 0. H is really the variable in this function, and the x is kind of just tagging along for the ride, almost like an arbitrary constant. Now, we're getting really, really close. And what I want you guys to notice is where we are right now, and I'm going to erase this as soon as I write it, but we are taking a limit as h approaches 0 of the cosine of h minus 1 over h. And if I go back to the first slide of these notes, that's a limit that we know. The other thing we're going to be doing here is taking a limit as h approaches 0 of the sine of h over h, which is also a limit that we know. So now maybe you guys are starting to see why we split this up the way that we did. Now I'm going to take some liberties here, guys, because I'm already spending more time on this than I need to, but here goes. f prime of x then is going to equal. Remember that this sine of x, because it doesn't contain an h, is essentially a constant that can be pulled out in front. So this is now going to become sine of x multiplied by the limit as h approaches 0 of cosine of h minus 1 over h. And from that first slide, that limit is 0. Plus, now we're doing the limit of this term right here. Well, again, the cosine of x is unaffected by h approaching 0, so I can pull that out in front. And now the limit as h approaches 0 of sine of h over h is equal to 1. I didn't write the limit as h approaches 0 anymore because I actually have gone ahead and put the 0 in for h. And now, guys, as you look at this real quickly, I think you can see what happens. Sine of x gets multiplied by 0. That's just gone. And the cosine of x gets multiplied by 1, which just equals cosine of x. And everybody, that is our answer. So back to slide number 2. I asked you to verify this in the box there, everybody, up above. We just found, you guys, that the derivative with respect to x of sine of x, come on now, is equal to, come on, struggling here, guys, is equal to cosine of x. Boy, that looks terrible. All right, let me try that again there, guys. So that derivative of sine of x is equal to cosine of x. That's a little better. Now, that is an identity that you guys may have remembered from last year if you learned it, but you may not have. Guys, the derivative of sine of an angle is equal to cosine of the same angle. And this work verifies that. Now, real quick, let's talk about that word verify again. I also want to verify this one graphically, just because I think it's kind of cool. If the original function right here, which I graphed on the calculator because I wanted this to look good, you guys, if the derivative, the original function is sine of x, we think we have learned now, everybody, that the derivative of this function is just equal to cosine of x. Well, let's play around with this the way that we did in section 3.2. Anywhere that there's a horizontal tangent on the original function, we know that the value of our derivative has to equal 0. Well, the original graph, sine of x, looks like it has a horizontal tangent right here, and right here, and right here, and another one right over here. So at all 4 of those spots, the value of our derivative, or the slope of our tangent, would have to equal 0. There, and there, and there, and there. Let's take a look at a couple of other spots. If I were to draw a tangent line to the original graph of sine of x, maybe right here at the origin, I'm asking you guys to guess right here what the slope of that tangent is. Well, it sure looks like it's positive, and it sure looks like it's going up at about a 45-degree angle. That means that the slope of that tangent is 1, so the value of our derivative at x equals 0 is 1 as well. Right here, let me go back to green here, everybody. Right here at x equals pi, the slope of our tangent looks like it is -1. So the value of our derivative then would have to be -1 as well. The same thing happens over here at negative pi. That slope looks like -1 as well. And now if you look at that arrangement of red dots, I'm thinking you guys probably recognize what's happening here. It kind of looks like, if I connect those red dots, I'm getting a curve that looks a little something like this, which looks an awful lot like the graph of cosine of x. So what we just did right here doesn't prove anything. This work that we did here and here, that proves this fact, that the derivative of sine of x is cosine of x. But this graphical exercise kind of supports that idea. All right. Now, we could do that for the other 5 trigonometric derivatives, but to do so, A, would take a ridiculously long time, and B, would require a whole bunch of trigonometric identities that you guys don't know, and frankly, I don't know, and it would get much, much messier than what we did there before with sine, which was already messy. So, I hate to do this, but we're going to go ahead and just write down the 6 trig derivatives, and I'm going to ask you guys to trust me on this one. Here we go. The first one we've already done, guys, that the derivative of sine of x is cosine of x. Now, I do think it's important, guys, that you get this right in your head. You're all going to be tempted to take shortcuts and just say that the derivative of sine is cosine, but I really would encourage you to start saying the full sentence. The derivative of sine of any angle is equal to cosine of the same angle. That's going to become important later on in section 3.7. All right, moving right along here. This is one I do want to come back and verify in a moment, but for now we'll just write it down. The derivative of cosine of x is the opposite of sine of x. We'll talk about that one a little bit more. The derivative of tangent of x, everybody, is secant squared of the same angle x. Okay, moving right along here, over onto the right side, the derivative of cosecant of an angle is the opposite of the cosecant, of that same angle multiplied by the cotangent of that same angle as well. So that's a minus cosecant of x, cotangent of x. But guys, it's incredibly important that you have the x in both spots. What I'm about to write, negative cosecant cotangent of x, this makes no sense mathematically. You should never be writing a trigonometric ratio without an angle that follows immediately after it. Cosecant by itself is gibberish. So we really want to get into that habit right there of putting cosecant of x, cotangent of x, and that one's a negative. The derivative of secant of an angle x is secant of x multiplied by the tangent of x. And the last one here, guys, the derivative of cotangent of x is the opposite of cosecant squared of that same angle, x. Ta-da! There it is, everybody. Those are your 6 basic trigonometric derivatives. Believe me now, no, hear me now and believe me later, or whatever they say. That's where you're at. And these are ones that in a normal year, I would tell you guys you're going to need to have memorized. You would need to know them on the AP test. They're going to expect that you guys know this information and you don't have it just written down. Now, before we move on, this can seem a little bit daunting to memorize these 6 trig derivatives. 2 things I want to point out. Number 1, just have them next to you and use them as much as you can while you're doing homework and just try to make yourself say them out loud. You'll pick them up quicker than you think. But the second thing I want to talk about, there are some patterns that I think are interesting and worth pointing out in this particular table right here. I got to fix that because that looks horrible. All right, here's the first thing I want you to notice. There are 6 derivatives here. Notice how many of them are negative. The answer to that is 3, half of them. And furthermore, which ones are negative? The derivative of cosine is negative, the derivative of cosecant is negative, and the derivative of cotangent is negative. So what does that tell us, guys? All of the cosine, cosecant, and cotangent, all of the cos have negative derivatives. So that's kind of the first thing that I notice about this table. The second thing I want you to notice here, 2 of them, 2 of these 6 derivatives that we wrote in black are a single trigonometric ratio squared. Which 2 are that? Those are the derivatives of tangent and cotangent. Okay, so the tangent and cotangent, the 2 on the bottom, those are the ones that are squared. And then lastly, 2 of these 6 derivatives involve using the same ratio that you started with. Which 2? This one right here. The derivative of cosecant of x contains a cosecant of x, and the derivative of secant of x contains a secant of x. All right, so there are some patterns that I think you guys will pick up on pretty quickly right here. But ultimately, those are 6 things that we need to have memorized. Real quickly, I said we weren't going to go back and talk about all of these, everybody, but what can I say? I lied a little bit. Let's talk about verifying this one here graphically. So the second trig derivative that we just wrote down in that last table said that if you were starting now with an original function of cosine of x, that's not what I wanted, that the derivative of that cosine of x would be the opposite of sine of x. So I'm going to go through this the same way. I just think this one's kind of interesting. Everywhere there's a horizontal tangent, here, 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 and actually here and here, the value of your derivative has to be 0. So I think that gives me 5 spots here where the value of my derivative, which is the same as the slope of my tangent line, would have to be 0. And now if we were to just guess, all right, at the slopes of the tangents right here, that slope looks like -1. Here looks like +1. Here it looks like -1. Here it looks like +1. So if the slope of my tangent tells me the value of my derivative, then here at -3 pi over 2, my derivative is -1. Here at -pi over 2, we're at +1. Slope of the tangent at pi over 2 was -1, and at 3 pi over 2, it looks like it's back to +1. And again, I think you guys know what to do when you see this orientation of all the red dots right here. we're going to go ahead and connect those dots and make a nice, smooth trigonometric curve. And what I'm hoping you guys recognize is it looks just like the sine graph, except the real sine graph goes up into the first quadrant and down and does something like that. What we're looking at now is the reflection of that graph over the x-axis, which is the opposite of sine of x. So again, that doesn't really prove anything, you guys, but I think it verifies a notion that we already had right here, which is that the derivative of cosine of an angle is equal to the opposite of sine of that same angle. All right, let's knock out 3 quick problems, guys, and then I think that's about all we need, and you guys are going to be able to get started here pretty quickly. So we're going to find the derivative of each one of these functions right here. And I'm not sure what that little dot is doing right there. There we go. All right, what's going on here? So the original function is x squared cosine of x, and we've got to come up with the derivative of f taken with respect to x. Well, one of the things I've said earlier in the chapter that you guys are going to have to get good at is recognizing when a rule needs to be used. And right here, our function isn't just strictly trigonometric. There's also this little polynomial right here, and they are being multiplied by one another. This is x squared multiplied by the cosine of x. That means that f is a product function. It's a product of 2 other individual functions, both of which contain your variable x. And for that reason, f prime of x is going to require the product rule. So here we go, guys. First factor is x squared. I thought it was x squared. Come on now. Here we go. You go away, you go away, you go away. Uh-oh. Okay, let's try it again. Nope, that just doesn't want to work right there. X squared, there's the first factor, multiplied by the derivative of the second. And the derivative of cosine of x is negative sine of x. I'm going to put the negative out in front and then just multiply the sine of x right there because I think that looks a lot better. Okay, so that's the first times the derivative of the second, plus the second factor, which is the cosine of x multiplied by the derivative of the first, which is 2x. And guys, it's not wrong to put the 2x here, but you've got to be careful because I think a lot of people are tempted to multiply the x and the 2x together to make a 2x squared. That is not what's happening in this case. So you could get around that. Let's do this again. You could get around that by putting a parenthesis around the full cosine of x, but I think the much better plan is to put the monomial 2x out in front of the trigonometric ratio, and that is where we are at. Okay, so that's what we've got. Now the question would become, everybody, is there anything that we can do to simplify this expression? The only thing I could really think of would be factoring out an x. All right, I wouldn't even write this down if I were you guys. You could pull out an x and make this a negative x sine, come on now, sine of x, and then simply a plus 2 cosine of x. But the question becomes, is this way of writing it better than this way of writing it here? I really don't think that it is. Factoring is not the same thing as simplifying, and I don't know that that made things better. So actually, guys, I think we're about done right here with this problem. I don't think there's a whole lot we could do to write that in a better manner. Okay, so I just wanted to illustrate there that sometimes the product rule does show up in some of these other derivatives that we're working on. Let's move on to a second example here. Y equals sine of x over cosine of x. Well, like we just talked about in the last problem, the product rule sometimes shows up. In this one, sine of x is being divided by cosine of x. So if we want to find dy dx, we are going to need the quotient rule. And let's run through this one. Quotient rule, which I'm sorry to say, a decent number of you got wrong on your quiz earlier on in chapter 3. The quotient rule starts with the denominator times the derivative of the numerator. Some of you are getting that backwards and you're starting with numerator times derivative of the denominator. But let's do it again. We start with the bottom, which is cosine of x, and we multiply that by the derivative of the numerator. And the derivative of sine of x is cosine of x. So it's bottom times derivative of the top minus the top, the numerator, which is sine of x, multiplied by the derivative of the bottom. And the derivative of cosine of x is the opposite of the sine of x. Okay, so there's your numerator now. Bottom times derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And you could write this as cosine of x in parentheses, quantity squared, but all the cool kids out there, guys, are going to write it as cosine squared of x, and I don't want you to get laughed at when you go to college. So where are we right now? Now I think we can do a little bit of simplification. The first term in the numerator, as I'm sure you noticed, is cosine of x times itself, which can be rewritten as cosine squared of x. The second term now is a sine of x times a negative sine of x, which would be negative sine squared of x, but we're subtracting that. So that's actually going to become a plus sine squared of x all over cosine squared of x. Now, I certainly hope at this level none of us are thinking that we can do this. You cannot cancel a term of the numerator. You can only cancel a factor of the entire numerator. So no, we are not doing that. But what I am hoping you guys noticed is that that numerator is something special. Your most basic Pythagorean trigonometric identity, everybody, says that cosine squared of any angle plus sine squared of any other angle is always equal to 1. I should have said sine squared of the same angle, excuse me. That numerator is automatically going to become a 1. And the cosine squared of x just stays on the bottom. And now what I'm hoping you guys recognize is that 1 over cosine squared of x is the very definition of secant squared of x. And that's not going to simplify any more than that. That, everybody, secant squared of x is the derivative of sine of x over cosine of x. But I don't know if you guys recognize it or not. There's a reason that I gave you this problem and a little bit of a joke for what's going on. If you notice the original expression right up here, sine of an angle divided by cosine of the same angle, that, everybody, is the very definition of the tangent of the angle x. Sine of an angle divided by cosine of the same angle is tangent of that angle. So look at what we just proved, everybody, that the derivative of tangent of x is equal to the secant squared of x, which is exactly what we wrote down in this box right over here, that the derivative of tangent of x is equal to secant squared of x. So, tricked you. We did actually verify one of those. Now, this question always comes up. Mr. Fontana, if that problem showed up on a test, do I have to do all of this work right here? Or if I recognize that the original expression can be rewritten, and then I can take the derivative of that rewritten form and come up with the answer much faster, will I get full credit? And the answer for that, absolutely, you will get full credit for that. In fact, I will be impressed that you took advantage of some background information that you had and that you remembered, and you used that to your advantage so that you didn't have to spend a whole lot of time doing a whole bunch of busy work right there. All right, so good for you if you did notice that. Just something that I wanted to point out right there to kind of verify that tangent derivative, but also to give us a little practice with the quotient rule within these trig problems. And the last problem I've got for you here, guys, this is the full, the whole 9 yards. We're going to go ahead now and find the equation of the tangent line to the graph of y equals tangent of theta times secant of theta, evaluated here when theta is equal to pi over 4. Okay, so to do this, everybody, there are some things that we need to know. But the most important thing to understand is that for the equation of a tangent line, we need a point on the line, and we need to know the slope of that tangent. Well, the slope of the tangent is going to come from the derivative. So if we named this original function y, I'm going to get lazy here and just call this one y prime, and here we go. Tangent of theta is being multiplied by the secant of theta. We're going to need the product rule to find this derivative. So the first factor here, as it was, is the tangent of theta. That gets multiplied now by the derivative of the second factor. And the derivative of secant theta is secant of theta times tangent of theta. And I don't know, it might help you to put parentheses around that. So that's first times derivative of the second. Gotcha. Plus, the second factor now which is the secant of theta, multiplied by the derivative of the first. And the derivative of tangent theta is secant squared of theta. Again, not really necessary, but if you want to put parentheses there to indicate that those are your derivatives, okay, you're in good shape. So we're moving right along now, guys. This is y prime would equal, and to clean this up a little bit, I guess this first term right here could be rewritten now, you guys, as tangent squared of theta times the secant of theta, okay, plus, and secant times secant squared, because it's all the same angle, would just be secant cubed of theta. All right, that's probably as much as we're going to do here now, you guys, to try to clean that up. So now, if we had that, I think that's probably fine. We're going to go ahead now and evaluate this derivative at this point in question. So this is going to be y prime evaluated when theta is equal to pi over 4. All right, and let's see what we can do here. What I'm really hoping you guys remember is that pi over 4 is in the first quadrant, and it's a 45, 45, 90 triangle right over there. Tangent then at that spot is going to be 1. So the tangent of pi over 4 is 1. That's going to get squared inconsequentially, and we're going to multiply that by secant at that same angle. Now, secant is the reciprocal of cosine. Cosine, your x-coordinate, is root 2 over 2. Or, before you rationalize that, it's 1 over root 2. Secant is the reciprocal of that, which is just going to be the square root of 2. Plus, and now we just did this, the secant of pi over 4 is the square root of 2, and we're going to cube all that. Oh, this is kind of ugly, Mr. Fontana. So where are we now? We're at the square root of 2. The 1 doesn't really matter. Plus, and root 2 cubed is going to get us a 2 root 2. Putting all that together, guys, that's a 1 root 2 plus a 2 root 2, 3 times the square root of 2. That's y prime of pi over 4. That, everybody, let's make a note, that is the slope of our tangent. Okay. What else do we need to know? We also need the point of tangency. And the point of tangency comes not from y prime of pi over 4, but just the original function, y, evaluated at pi over 4 as well. So I'm going back right up here, guys, and here we go. Luckily, we've done most of this work already. The tangent of pi over 4 is 1, and the secant of pi over 4 is root 2, so that just gives us an ordered pair here now, everybody, of pi over 4, that's your x-coordinate, or really your theta coordinate, and then root 2, that's your y-coordinate. So there, that is the point of tangency right over here. And now that we know slope of the tangent and point of tangency, I'm going to start a new page here, guys, and now we're going to go directly into point slope form. So that is going to be y minus our y-coordinate, which was root 2, is equal to our slope, which was 3 root 2, glad I looked because I was about to write 2 root 2, times x minus the x-coordinate here, which is going to be pi over 4. So there's the equation, everybody, in point slope form. Again, normally they want it in solved for y. So the cheap way to do that is to just write it as y equals. Leave this exactly the same. 3 root 2 times the quantity of x minus pi over 4, but take this k value now and just put it at the end. So that's a plus root 2. If you did want to distribute that, you're certainly welcome to do it. I just don't know how much is really going to happen to benefit us here, but let's see. Y would equal a 3 root 2, that's bad, 3 root 2, and then we would multiply that by x minus, nothing simplifies here, so this would be like a 3 root 2 times pi over 4, and then a plus root 2 at the end. And guys, I really don't see any point in trying to put those like terms together. So, boy, that's an ugly problem. I'd be really tempted to quit right here. I think at that point you could kind of look at it and say, you know, I could distribute the 3 root 2, but nothing nice is really going to happen. And I would say that that right there is probably the way to go. If you care, all right, what's going on here, guys? This, of course, was point slope form right here. This second line here is something called point slope equation. It's really the same thing, but we did technically solve this for y without really distributing the slope inside there. All right, guys, that's everything I wanted to cover with you on 3.6. Hopefully it's not too bad. Let's give that homework assignment a try. Let me know if you guys have any questions, and good luck.